All right, in this video, we are going to take a look a little bit about how to do some calculus with this polar coordinate setup. So really two main topics. How are we going to find slopes of tangent lines, and how are we going to find area under the curve? Let's go. So for the slopes of tangent lines, again, we are really focusing on this derivative, dy over dx. There are other derivatives that we can look at that might be helpful to think about, right? We can think of dr over d theta, because remember, these polar functions are functions of theta. There we go. So we could go ahead and just differentiate this thing and try and figure out like what r prime is, and maybe that's helpful, but those are different than the slopes of the tangent lines. When we think about slope, we're still thinking rise over run, change in the vertical component over the change in the horizontal component. So again, we have these functions that we're going to call like r equals f of theta or r of theta or whatever. But what we want is dy over dx. It's easy enough for us to go ahead and find dr d theta. This is going to be the rate at which the radius, the distance from the pole, changes as theta increases. So as you move around this way, do you go out or in or things like that? That's really what this is doing. That's not a slope of a tangent line, which is what we want, dy over dx. So you can imagine we're going to use the chain rule again. This is our chain rule that we have, and we're just going to shuffle this around to say that dy over dx is really dy over d theta over dx over d theta. So we just have to differentiate x and y both with respect to theta and then look at this fraction here. Now with parametric stuff, that was easy because our x and y's were written as functions of that parameter t, but now we don't necessarily have that. We do have that x and y are written as functions of r's and thetas, though, and r is a function of theta. So we really do have that x is a function of theta and y is a function of theta. It's just that they take these forms instead, where r can change, right? That's just going to be whatever's defining the polar curve. So we can go ahead and look at the derivative of this thing. Because r is a function of theta and sine theta is a function of theta, we have to use the product rule. So we'll look at the derivative of the first term, r prime, times sine theta, plus r times the derivative of sine theta. There we go. And then we can do the same thing with the product rule on the very bottom. R prime cosine theta minus r sine theta, where again, I'm using this r prime to really represent dr d theta, where r is a function of theta. So we'll just have to do some differentiation there. But really, we're really doing the product rule on this. And we're just going to use this definition of x and y over and over and over again. So let's take a look at this polar curve and let's try and figure out where we have horizontal tangent lines. We know what we're really thinking about here is that dy over dx is equal to 0. If you want to think about what this curve looks like, we can just try and imagine what happens to r as theta increases, right? We know that when theta starts at 0, sine theta is 0, and so that means our r is 1. So we're going to be here. And as we increase, sine is going to get bigger, meaning we're going to keep subtracting stuff until sine at theta equals pi over 2 is going to be 1. So we have this 1 minus 1. So we're going to have another point here. And it's going to look something like this. And then what we'll notice is that after that, our sine values are going to be negative, and so we're really going to be subtracting these negative values. That's going to be getting us some nice big radii out of this thing, right? So we're going to still have things that are close to, or sorry, not negative. They're close to 1, sorry. But then we get back to 0 eventually, so it's going to be here. And now we've switched to having negative values for the output of sine, so we have 1 minus these negatives, and that's being positive. Or adding more, so we're going to get further and further and further away until our largest value here is at 2, and then we're going to kind of circle back around. This is a pretty bad picture, but if you just fire this thing into Desmos or other graphing calculators or things like that, you can see a better picture of this. This curve is called a cardioid. That's the shape that we have. It's a pretty popular one that shows up in a lot of different instances, but anyways, that's what this is. So we're looking for horizontal tangent lines on this. Technically, we don't really care a ton about what this looks like, or we don't have to care a ton about what this looks like. We know we want to find dy over dx, and we know that that's dy over d theta over dx over d theta, where x, remember, was r cosine theta and y was r sine theta. Now, this is what we mean by product rule. What we've got now is that x is 1 minus sine theta times cosine theta, and y is 1 minus sine theta times sine theta. And so we're going to do a product rule where we split things up into these two pieces. Okay, so what we have now is r prime times cosine theta. So that's going to be the derivative of 1 minus sine theta. That's going to be 0 minus cosine theta. So this is negative cosine theta times cosine theta plus 1 minus sine theta. Oops. I'm doing x. I got to put this in the denominator. There we go. So this was negative cosine theta times cosine theta. There we go. And then it's our derivative of cosine, which is negative sine, times 1 minus sine. So I'll say minus 1 minus sine theta, sine theta. Cool. In the top, we're going to do the same sort of product rule here on y. So I'm going to look at the derivative of 1 minus sine theta. That's again going to be negative cosine theta times sine theta. And now I'm going to look at 1 minus sine theta times the derivative of sine theta, which is cosine theta. Cool. This is our derivative, and what we want to do is set this thing equal to 0. So you can try and look for some like common factors to pull out and reduce this thing, but it doesn't look like we can really do much, right? We can't factor anything that nicely out of the denominator. So what I'm going to do then is just look at where this numerator is equal to 0, right? We can go ahead and do that. So let's take a peek. I am going to try and be a little bit careful and make sure that this denominator doesn't equal 0 when I find this stuff. So let me just go ahead and figure out what's going on here. I'm going to do some distributive property. So I'm going to get a factor or a term that's cosine theta. And then notice when I multiply this thing out, I also have another negative sine theta, cosine theta. So I'm going to have two factors of those. Let's say this is cosine theta minus 2 sine theta cosine theta. And then in the denominator, I've got negative cosine squared theta minus, I'm going to leave this as 1 minus sine theta sine theta for now. Okay, so in the numerator, you can notice that this really becomes cosine theta times 1 minus 2 sine theta. And then if we set this equal to 0, it becomes pretty easy to see what's going to happen. When we set this equal to 0, that means cosine theta is equal to 0, or sine theta is equal to a half. Well, cosine theta being 0 is a nice thing that we can think about. Let me draw my unit circle. This is a really bad one, but oh well. Cosine is 0 right here and right here. But what I want us to notice is that at this point, sine theta is 1. So that means that this is going to be 0. So this is equal to 0 at theta equals pi over 2, meaning the two values that I get here for cosine theta equaling 0, pi over 2, and 3 pi over 2, this one's not going to do it. We don't actually have a horizontal tangent line there because our derivative doesn't exist, which we can see. That's this point right here, right? There's clearly not a horizontal tangent line there. But we can see down here at 3 pi over 2, look at that. Horizontal tangent line. Great. Now we need to find where is sine equal to a half. Well, on our unit circle, that's at these 2 points right here and here. That's where the y values are equal to a half at those angles. And so if we're trying to figure out what those angles are, that's going to be pi over 6, and this is going to be 5 pi over 6. And you'll notice that those values have no problems where our denominator is not going to be 0 there. And that's right there, pi over 6 and 5 pi over 6. So those are our 3 points where we have these horizontal tangent lines here. X equals pi over 6, 5 pi over 6, or 3 pi over 2. Again, we'll just notice that we had to throw out the pi over 2 value because our denominator of this derivative was equal to 0. Our denominator doesn't actually exist there. Awesome. We can do a whole bunch of other stuff with derivatives, but it all ends up being those same kinds of computations. Let's think about definite integrals instead. What we're going to need to do here is build up a completely new way of defining the Riemann sum construction. We used to use rectangles to do this, which made sense when we were in a Cartesian coordinate system, because that's a rectangular coordinate system, but now we're not, right? We're in this circular coordinate system. So let's just say we have some sort of a polar curve that does something like this. I don't know, who cares? And let's say we're trying to figure out the area right in here, this kind of shaded in region. What we're going to do is the same basic idea of a Riemann sum, but instead of using rectangles, we're going to notice that we're going to subdivide this into these weird kind of triangular sectors. These looking like pizza slice sectors here. And so instead of approximating using a rectangle here, what we're going to do is approximate using a sector from a circle, where really maybe our curve does something like that, but we're going to approximate it this way. The nice thing is that there's a good area formula for this. The area of this is half times the radius squared theta, where theta is this angle that we have. Cool. So that's the area of each of our pieces. Now, r squared, that's going to be some sort of randomly picked value of r, right? And so that's really going to be like f of theta sub k star that we're going to use for r. We're going to just pick a value, just like we use some randomly picked value in our rectangle. Maybe it's the leftmost point, maybe it's the rightmost point, but maybe it's just some point in between. It doesn't really matter. And then what we're also going to notice is that instead of calling this theta, we're going to call it a change in theta. This is going to be delta theta, where delta theta is the change here. We're going to subdivide these equally, just like we had a width of a rectangle being delta x. Now we're going to say we'll just keep going a tiny little bit of an angle until we get the whole angular span here. Just like when we added those tiny little widths, we got the whole width span of a rectangular setup. So this is our area formula. All right. So if r is some function of theta, then the kth sector is half f of theta sub k star squared times delta theta. And then we can add those all up to get an approximation of the area. And we add a limit to this thing to get a definite integral. Great. This looks good. This looks like what we did at the very beginning of the semester when we used Riemann sums to build integral formulas for things. So this should not be too much of a surprise, where here alpha and beta are just the beginning angles and ending angles. We use the Greek letters to remind ourselves that those are angles. So here's our big setup. For some region bounded by the graphs of r equals f of theta and r equals g of theta, I'm adding two graphs now, between these two angles where f and g are both continuous and one of them is further out than the other, right, on that interval, then we just look at this difference. This is almost exactly like your area between curves formula, except now we have this half function squared in here. And that's because instead of rectangles, where we look at width times height, we're looking at half times a radius squared times an angle. So that's just from this circular sector area formula. All right, so let's go ahead and do this. Let's imagine this curve, 3 cosine 4 theta. This is going to be a nice little flower curve, and we can try and find the area bounded inside one of these petals in our curve. Just to show off what this curve is, I went ahead and I put this on Desmo, so let me show you that. You might not be able to see it here, but you can see my interval for theta is between 0 and t, and I'm just going to change what t is. So this is going to be kind of a parametric polar curve, but it's to show you how we would draw this as our angle t increases. So let's go ahead and do this. Oh, this is pretty cool, right? Doesn't this look like one of those little spirograph things? So you can see our cosine value starts up at 1 and goes back to 0. And then at this angle, what's that, like pi over 8, right? It's going to get negative. And so really that would be like this petal up here, but it's flipped down into this other quadrant because our radius is negative here. And then it flips back up as we keep going. It's a pretty cool little graph, but you can see how it looks like a flower here. So let's just show you the whole thing. this is our curve. After 2 pi, it just keeps repeating here. And you can see this looks like a nice little flower. And maybe we want to find the area of one of these flowers. If you want, you could go ahead and say like, all right, we start here, and you could try and figure out how we define one of the flowers, what the angles are for getting one of those. But what we'll notice is that the flowers, or the petals, kind of start and stop when we cross through the pole. So what we could do is just look and see, when do we actually cross through the pole? So what are the bounds here? That's when r equals 3 cosine 4 theta is going to be equal to 0. So we can go ahead and say this is when cosine of 4 theta is equal to 0. And that's when 4 theta is equal to these angles, right? This is negative pi over 2, and I'll throw the old dots in here, 3 pi over 2, etc., etc., etc. And so theta is going to be negative, I'll put the negative 3 pi over 2 in here as well. So this is negative 3 pi over 8. There we go. Negative pi over 8, pi over 8, 3 pi over 8. And you can see how we just keep counting up in there. So what I'm going to do is just grab these ones right here. I'm going to say, let's take a look at this loop. This loop is, if we draw this thing all the way out, it's this right here. We can go ahead and look. Negative pi over 8 up to pi over 8. That's the petal that we're looking at here. You could pick any bounds that you wanted as long as it only includes one petal here. But now what we're going to do is say this area is going to be an integral from negative pi over 8 up to pi over 8 of half r squared d theta. So this integral is half the integral from negative pi over 8 up to pi over 8 of 9 cosine, maybe I'll just say 9 halves. That'll be easier for me. Of cosine squared 4 theta. And this is something that we know how to do. We can integrate this. You could also use some symmetry here for the cosine function because we're squaring this thing. So this is going to be even symmetric. So if you wanted, you could say that this is really 9 times the integral from 0 to pi over 8 of cosine squared 4 theta. If you think about your picture, what we're really doing then is saying we're looking at just this section, and we're just going to multiply that by 2. Right? We're going to double the size of that thing. So that's what's really going on here. Again, I'll let you finish this integral out. We can do this. We're just going to end up doing one of those power-reducing half-angle formula things on here to get that cosine squared written in terms of just cosines, and then we could integrate things like normal. There's really no difference for how we would finish this problem. So that's how we could set this thing up. Here's another good one. We can find the area bounded between that cardioid, 1 minus sine theta, you remember that one? And then r equals sine theta. That's a circle, right? This is a circle that's going to be centered on the y-axis at 0, 1, right? And it's got a radius of 1. So we've got something that looks like this. There's our circle, and then here's our cardioid. I don't know, something like that. And we're looking at the area bounded between these things. So right like here. That's a pretty bad picture, but oh well. If you wanted to see a bit of a better picture of this, again, you could just throw this into Desmos, and there we go. And again, we're looking for this area trapped in between here. So we can see we need to find some bounds where, remember, we started here with our cardioid, and where we cross our circle here, and then this is still on the inside here, and then now when we cross through. So we have to find those two intersection points, right? We have to find what are the values of theta here and here. There's really a couple of spots where they're equal. We don't really care too much about that middle one. So what we want to do is, again, find our bounds by looking at where sine theta is equal to 1 minus sine theta. Where do these things intersect? And now we can go ahead and say, well, this means that 2 sine theta is equal to 1, and so that means that sine theta is equal to a half, right? And so again, we've got pi over 6, 5 pi over 6. So our area is going to be an integral from pi over 6 up to 5 pi, over 6 of half times, now we got to think about this, it's the outer one squared minus the inner one squared. Now in this case, what we mean by outer is which one has the bigger value of r, and that's going to be our circle as we move around. So what we're going to do actually is find this blue area with our integral, and then the red area should be easy enough to find because it's just going to be whatever's left over in the area of that circle, right? So again, we're going to think outer curve. That's where r is bigger. Here you can see r is really close to 0, and now r is going to be way up here on the circle. So we're going to say this is going to be sine squared theta, that's this one, minus 1 minus sine squared d theta. Now, that's not the area that we care about. This is the blue area, right? And so our real area is going to be the area of the whole circle. Now, that should be easy because we know what the radius of this circle is. The radius is 1. And so we know that the area of this circle is just pi r squared. It's just pi. So what we can do is say our red area then is going to be pi minus this integral. Half integral from pi over 6 to 5 pi over 6 of sine squared theta minus 1 plus 2 sine theta minus sine squared theta d theta. And you can see that stuff is gone now. And this should be a relatively straightforward integral to compute. Not too bad. And that's going to give us this nice little red area here. So finding areas between curves, we still have to do all the same kinds of things that we did when we were doing area between curves and Cartesian coordinates. Find intersection points, try and juggle which one is bigger than which, all that same kind of stuff here. But hopefully that gives you a bit of insight on what we're doing with this. All right, that's all we've got for polar coordinates. I think there's a little short video left with some conic section stuff, but most of the conic section stuff that we're going to do, I'm just going to put up on the course sites so that you can take a look at some cool animations and stuff like that.